Here we're going to consider a vertical piston cylinder assembly that is exposed to the atmosphere. So out here we have P naught, and inside we have an R134A blob. And also inside here we have a resistor. We know that the mass of the R134A is 0.8 kilograms. So we know M. And we also know that initially the temperature in here is -5 degrees centigrade. The piston is free to move without friction. We also know that there is a current passing through here, and that the current is 2 amps. So I here for our circuit is 2 amps, and the voltage drop across that resistor is 10 volts. So what's going to happen is that, and also we're told that state 1 is saturated liquid. So X1 means X is the percent of, or mass fraction of gas. There is no mass fraction of gas when it is all liquid, so X1 is 0. And then we're told that we're going to move to a state 2, and at state 2, everything will have changed from from liquid to gas. So X2 is going to be 1. And we're asked to find, in this problem, the time required, or delta T, probably more likely. So let's go ahead and write down some governing equations. Obviously, we can see that given two properties here, so we're going to be needing an equation of state, R134A, and we know that it's mixed the whole time. Right? It goes from saturated liquid all the way to saturated gas. In fact, if we wanted to draw this picture, and we'll do that in a second, what other equations could we be using here? We probably want to write down and use the equation for the first law, du dt equals q dot minus w dot, for time-dependent processes. So of course this is going to be we're going to have a table here. And then the next thing we probably want to write down, just as a kind of important, not sidestep, but an important opportunity to understand this problem physically, we're going to assume that the process takes place reversibly. So in other words, there's an ELF involved, and this is a reversible process that occurs not because of a force imbalance, but at equilibrium. So the sum of the forces here is equal to 0. So what we can do here is first take a look at just this force balance. So if we want to balance the forces on the piston head here, we obviously have the force of the atmospheric pressure. We have this force of gravity, and lastly we have the force of the R134A blob. And the first thing you should probably notice is that P naught, FP naught, and FMG, or FG, those are going to be constants. And if these things always balance, that means that FB must be a constant. So if these two are constants, then so must FB be a constant. So let's go ahead and plug in for what these are. We've done this over and over again. So P naught times A in the minus j hat direction plus mg in the minus j hat direction, plus force of blob, which is going to be pressure times area in the positive j hat direction, equals 0. So P is, not surprisingly, P naught plus mass of the piston, gravity over area. We don't really know these things, but what we do know is that it's a constant. It's a constant in this whole process. So what this has told us is that from this whole Newton's second law exposure, we've basically been able to tell that this is an isobaric process. All right, it's an isobaric process. The pressure is a constant in this process. And anytime we have isobaric, we probably know enthalpy will be convenient. Probably be, oops. Will probably be convenient. Okay. So let's go ahead and take a look at and try and really find out what this pressure might be. So we know that the pressure at 1 is going to be P naught plus mg on A, and we also know that that pressure will be the same pressure at 2. So if I can find that pressure, that gives me 2 properties at 2. And that's pretty good. How would I find that pressure? Well, let's draw the process, the isobaric process, as it will occur. What we know is that the pressure is going to stay the same, and we're going to have an increase in the volume, right? The quality is going to go from 0 to 1. Well, we know that V is basically equal to Vf plus x times Vfg. So as x increases, V goes up. So if I were to draw this in the PV plane, we have a vapor dome, and we have a constant pressure process occurring. And on that constant pressure process, we're also going to have a constant temperature, because P and T, P is a function of T in the vapor dome. They're dependent. All right, so this is V1, and really V1 is equal to Vf, and this is V2, and that's going to be equal to Vg, right? Because basically, recall, V equals Vf plus x times Vfg. So if x is 0, at state 1, it is 0. V1 is just equal to Vf. And at state 2, x1 is just equal, or x is equal to 1. So this is Vf plus Vg minus Vf, so the Vf's cancel out, you just get Vg. So that's pretty good. Where is all this happening at? At the temperature minus 5 degrees centigrade. So I can look that up in my, so all of this is at minus 5 degrees centigrade in the table. Let's take a look at what this means in terms of the first law. So the first law we've written down right here. It's not in terms of enthalpy, it's in terms of energy right now. So let's maybe try and change it. So I know, and this is where I have to kind of start, H is equal to U plus PV. I know that to start off with. This is the definition of enthalpy. Great. And so in this problem right here, I also know that W dot, that's basically equal to dW dt, we can recall. Or we could just say, what is dW? That's pdV, so it's p dV dt. Of course, the pressure is constant, isn't it? So it can go inside the derivative, ddt of PV, right, for isobaric. So this is only possible to be done when it's isobaric, right? So let's go ahead and plug this in. and in fact I want this to be a capital V. Excuse me. Let's go ahead and plug this in to the first law. So the first law is du dt equals q dot minus w dot, but w dot is d dt of pv. So I'm just using work, the first law, and the equation of state again. Let's bring it over to the other side of the equation. So what happens? I'm going to have that d by dt of u plus pv equals q dot. What is u plus pv? That's h. So if I know q dot, I can integrate this, and I can find out the time that things will take. So what is giving rise to q dot here? So q dot comes from the resistor, from, in fact, a steady state resistor. What does that mean? Let's take a look at the resistor here real quick. So the resistor is running at steady state. So if my control volume surrounds just the resistor, so the resistor here is what's happening, I can see, oh, what is the first law for this resistor? dE dt equals q dot minus w dot. Here I use E because a resistor is not a blob, so it has perhaps other types of energy besides just simply thermal energy. But it doesn't matter because it's zero. Why? Because this is running at steady state. How do I know? I'm assuming that it is. I've plugged it in and it's heated up, and now it's no longer changing with time. So it's just adding heat. In other words, q dot here equals w dot. So the work that I put into the resistor is equal to the heat transfer out. That's what this means. And in fact, for a circuit, if you were to go Google this, what kind of work rate do you have when it comes to this circuit? Well, it's just the current times the voltage. And how can I'll call it V tilde is the voltage. So 2 amps times 10 volts, and in fact a volt amp is a joule. So this is a unit, or I'm sorry, a watt. So this is an example of a work rate. This is the work rate, and this is the Q. This Q right here is the Q that's going out, so to speak. So Q is positive in. In this case, the work rate better be negative since I'm putting work in. So we want this to be a minus, right? So we're putting work in. We're putting the work of the power plant into the resistor, and it's heating it up, and then I'm getting heat transfer out. So this better be less than 0 to start off with, and that's why this negative sign shows up. Of course, I times V is only always going to be positive, so in order to know the sign of this, I need to figure out, am I putting work in or am I getting it out? I'm putting work in. The work rate is going in. So this is Q dot here, and this is the Q dot. We'll call this Q dot tilde as well, because of course this work rate is different than this work rate, isn't it? Because this is the work rate of blob, this is the work rate of the resistor, this is the Q dot of the resistor. So where is this Q dot of the resistor going? So if it's going out of the resistor, it's going into blob. So we could say that the heat transfer rate into the R134A is minus the heat transfer rate out of the heat transfer rate due to the resistor. Let's plug in. All right, so this number is positive. All right, this says that the heat transfer rate into my R134A is positive, and that's what I would expect. Heat is going in. Heat transfer is positive in, so heat's going into R134A here. And this is a constant, in fact. right? So in other words, right here, we've just shown that this is equal to I times V. Oh, V tilde, excuse me, not volume, but voltage. And this is a constant. So how can I integrate this? Well, integrating a constant is not difficult, right? This is a constant, so dH equals Q dot dt. Integrate once, I'm going to get that H2 minus H1 equals Q dot times T2 minus T1, which is just delta T. So in this problem, I have that delta T is going to be equal to H2 minus H1 over Q dot. That's going to be equal to M times H2 minus H1 over Q dot. And what is H2 going to be? Well, H2 is the enthalpy when I am all gas at minus 5 degrees centigrade. So that means that this is just Hg, and this is Hf. And subtracting the two gives me HFG. So M times HFG over Q dot, where Q dot is the voltage times the amperage, and the HFG here is looked up in terms of the temperature at minus 5 degrees centigrade. So at minus 5 degrees centigrade. The whole thing is isothermal because it's isobaric. So if the pressure can't change, the temperature can't either. And in this case, that's exactly the case. The pressure can't change, so the temperature can't either. So it's both isothermal and isobaric. And so the last thing you'd have to worry about here is that you'd want to make sure that you took volt times amps and you convert that volt amperage into you want to convert that volt amperage into kilowatts, because what you're going to look up in the text, HFG here, is going to be in kilojoules per kilogram per Kelvin. And I'm sorry, in kilojoules per kilogram, not per Kelvin. So that's how you do this problem.